Hello everyone and welcome to this lecture on system design principles. So this is an extension of the labs that you have already been doing so far, and this is to supplement the lab activity in fact. So as we have now done two experiments. So we have done the first lab, which was the calibration of the PT100 based Wheatstone bridge using the Peltier element. So with that you could actually measure the temperature as a function of the differential voltage of the Wheatstone bridge. So you have done that. Now the second experiment that you did was you followed up the Wheatstone bridge with an instrumentation amplifier. So you basically amplified the differential voltage you got from the Wheatstone bridge, and then you observed what was the transfer characteristic. So you had a plot which was temperature versus the amplified voltage. So you have also done that. Now the third lab, we were supposed to work on integration of the Raspberry Pi. So what we wanted to do was we wanted to take the amplified signal from the instrumentation amplifier and send it into the Raspberry Pi so that you could collect this information and do any calculation you wanted to do with it. And this requires the use of an ADC because the Raspberry Pi works primarily with digital signals. So you have to convert the analog voltage you are getting from the instrumentation amplifier to a digital signal. So now in principle I would have liked you to do this in the labs, but there were too many moving parts and I thought that maybe we could do it as a lecture demonstration instead of you doing it in the lab. Of course you are more than welcome to do it in the lab. I can show you the setup and you can also play around with it. But the focus of this particular presentation is to walk you through how you will design the system as a whole, not just the last block of the system but as a whole. And that is the primary purpose of this lecture, how to design a system. Alright. So if we want to attach a specific goal, the specific goal is we want to design a Raspberry Pi based temperature logger that can be used to measure temperatures between 0 to 40 degrees Celsius. Now I have specifically chosen this particular range because we are able to easily control the temperature of the Peltier over this range. And also the 0 is there because, well, you can actually arrive at a 0 condition for the Wheatstone bridge, and that's why I have put that 0 there. You will understand as we walk through the lecture, you will understand why this particular range of temperature was chosen. Alright. Okay, so the experimental setup, I am showing you already what you are going to finally see, or what was the final realized setup. So here you can see that this is the Peltier which is sitting in a water bath. You have got a thermometer which is connected to it, right? So you got a thermometer which is connected directly to the Peltier, and you also have the PT100 temperature resistor which is also mounted on the Peltier. That is coming into this Wheatstone bridge configuration here. The voltage from the Wheatstone bridge, the differential voltage, is now fed into this instrumentation amplifier. That instrumentation amplifier is being powered by two 9-volt batteries because you need a plus minus 9-volt connection. So that's being powered separately, and then the output from the instrumentation amplifier is fed into the ADC MCP3008, and this MCP3008 is connected to the Raspberry Pi. So you've got power supply connections and also the communication protocol connections, right, the SPI connections. So this is the total setup, and once you can write a very simple code on Thorny on the Raspberry Pi, and it will continuously be reading out the temperature values. So you can scale the temperature values or you can read it at the bit level. So we can see, now we'll go step by step and we'll see how we can arrive at this final configuration from scratch essentially. Okay, right. So the basic idea is, now we have done two labs where we have focused on the individual parts. So in the first lab we focused on how to build the Wheatstone bridge, what are its nuances. Similarly, we have done it for the instrumentation amplifier. The final block is the ADC which connects to the Raspberry Pi, but it is going to be useful not to think of each item discretely but as a system as a whole, and that is the system design approach we'll be talking about. So this is the whole block layout. So you've got the Wheatstone bridge which is connected to the instrumentation amplifier, which is connected to the MCP3008, and finally you have the Raspberry Pi. Right, and these multiple lines are to show the communication protocol lines. It's just illustrative. The other thing that I would like to say here is I'm using the Raspberry Pi to power the Wheatstone bridge. So I'm using one of the GPIO pins on supply voltages to power the Wheatstone bridge itself. Okay. So the question is, how are we going to make this whole chain so that the whole thing works together? Because you've got different parameters for the Wheatstone bridge, you'll have different parameters for the instrumentation amplifier, like the gain, what kind of supply voltage you can supply to it. For the Wheatstone, it's what resistors you will use, what input voltage you will provide. For the MCP3008, again, you have its own restrictions and its own constraints. So the question is, where do we start? Okay, and the simplest answer is we work our way backwards. Okay, and what I mean by that is we start from the last block which connects to the Raspberry Pi. And this is one simple way of working at it, because ultimately no matter what you do here in the first two blocks, if the first two blocks don't feed in the right kind of signal into this MCP3008, then all of the work that you are doing is moot. So this can be taken as the starting bottleneck, and you can work your way backwards from there. Okay. Once we work our way backwards, if we find other bottlenecks, we'll adjust along the way, but this is kind of a tried and tested approach, and it has worked for me all the time, right? So I start from the last block and then I work my way backwards. Okay. So let's see what that actually implies. Okay. So that's the last block, that's the MCP3008, and you have the chip pinout, right? So these are the chip pinouts. And as I've always mentioned, if you have a chip, the first thing you should do is to find the data sheet for it, and once you find the data sheet for it, you can actually find the maximum ratings for it. Okay, so once you find the maximum ratings, you will see that the maximum voltage that you can supply, the maximum supply voltage, is of the order of 7 volts. What this essentially means is all the other inputs and outputs will range in this value, and these are the maximum limits. So you cannot supply a VREF more than 7 volts, like 7.6 volts, or you cannot supply, even for the channels, you cannot go beyond that 7 or 7.6 volts, right? So what this means is we have a bottleneck here. The bottleneck is the maximum voltage that can be supplied to the ADC limits the maximum voltage that can be supplied to the VREF and also to the other channels. Okay, so this is the first bottleneck. So what does that mean? This in addition means that there is a gain constraint on the instrumentation amplifier also, which means that the signal that is coming out of the instrumentation amplifier cannot be more than 7 volts. Basically this limits the gain, right? So now we are working our way backwards. Now, since we are powering the MCP3008 using the Raspberry Pi, what I'm actually going to do is I'm going to connect the 3.3 volt pin, because in the present purpose this is in a field C later. Why, right? You can use the 5 volt pin. There was a slight problem with the 5 volt pin, and that's why I decided also to use it with the 3.3 volt. The 3.3 volt was more stable. Okay. And also because we are powering the Wheatstone bridge with another 3.3 volt pin, so it kind of makes logical sense to just limit the MCP3008 to this range. So that's what we have done here. Okay. So once we have done that, now we have this constraint equation, right? So we'll keep this aside. Okay. Now let's come to the Wheatstone bridge. Now we'll work to the final block. So in the Wheatstone bridge, ideally what we want is we want to operate it in the most sensitive mode, and in the most sensitive mode we want all the resistances to be more or less equal. So what we have done here is we build the Wheatstone bridge like this, where we have got the PT100 here, which is roughly in the range of 100 ohms, 100 ohms at 0 degrees Celsius, but 100 ohms roughly in that range, doesn't vary too much. So we build a Wheatstone bridge which has 3 more resistances, which is of the order of 100 ohms. So in principle this is what we would like to use, but there is a problem. The current draw, if you calculate the current draw from the Raspberry Pi, because we are powering the Wheatstone bridge using the Raspberry Pi, the current draw will exceed 16 milliamperes if we just directly use this. Because from a given pin in a GPIO, from a given GPIO pin, we cannot draw more than 16 milliamperes. Okay. So what we do here is a very simple fix, which is put a current limiting resistor. So here I have chosen 500 ohms, and when I put this 500 ohms in, the current is limited to even below 5 milliamperes. So we are pretty much working in a very safe configuration. We are not drawing out a lot of power. So this is pretty good. Alright. So once we have that, we can also estimate what will be the typical voltage values. So we can vary the PT100 resistance over a given range and see what will be the typical value. And if we do a quick simulation, we see that it is in the range of 0.02 volts, right, 20 millivolts. So the output from the differential voltage output from the Wheatstone bridge will be of the order of 20 millivolts, right? So that means that now we can use that information to calculate how much gain we need to provide to the instrumentation amplifier, because we have got this constraint relation, right? So we can use the formula for the gain resistor, which is provided in the data sheet for the INA126, and we also additionally use the constraint equation, which is this 3.3 volts. The gain from VBD cannot exceed 3.3 volts because that is the reference voltage we are providing to, that's the supply voltage we are providing to the ADC, and also that is the reference voltage. So we will keep it, the gain, in such a way such that the maximum voltage that's going to come out of the instrumentation amplifier is going to be less than 3.3 volts, right? So that is roughly, now if we take this into account, that is roughly in the range of 200. So we need a gain of 200 on the instrumentation amplifier. And again our data sheet comes to the rescue, and in the data sheet you have this very nice table, and you can very quickly pick out this resistance value, which is around 400 ohms. So that is the resistance, the gain resistance you will provide to the instrumentation amplifier, right? So now we have all our parameters fixed, right? So what that means is, in this experimental configuration, if we just focus on our circuit configuration, so on the first end we have the Wheatstone bridge. So here you can see the current limiting resistor, and this is the Wheatstone bridge configuration. This is the PT100 resistor which is coming in and attaching to the Wheatstone bridge, and now you have the outputs, the VB and the VD outputs, which are connected to the instrumentation amplifier. So the instrumentation amplifier has now been provided with the gain resistor, the differential inputs are provided, the supply voltage is given using the batteries that you see here, and then the output now from the instrumentation amplifier is fed into the ADC, which is the 0H channel, or the first channel, the first pin or the 0H channel of the ADC here. And the ADC is now connected to the Raspberry Pi, the power supply pins are indicated here, and here you have your communication channel pins, right? So everything is now put on this breadboard. The other thing is, you have this, because we are using two batteries in series, you have a common pin. That common pin is also attached to the common ground of the Raspberry Pi. This is to ensure that all voltages are measured with reference to the same voltage. So you are not leaving any grounds floating, you are just connecting it to the ground of the Raspberry Pi, which is in addition connected to the ground, the earth ground. Alright. Okay. So now that we have this configuration ready, what we are going to do is we are going to measure directly the output from the Wheatstone bridge, even before we are connecting it to the instrumentation amplifier. And if you use the multimeter, if you use a conventional multimeter and you measure the output from the Wheatstone bridge, and we are actually varying the temperature of the Peltier element, and we are varying it over the range of 25 degrees Celsius to 35-ish, right? Now you see that it's rather discrete and step-like, right? And it's step-like because the multimeter has got a poor resolution. The multimeter resolution is of the order of 1 millivolt, and that's why you see the step-like evolution of the VBD voltage. Okay, what this essentially means is we actually need an instrumentation amplifier to expand that range, to amplify that range so that it falls within the resolution of, we can make good quality measurements with the multimeter itself. Alright, so that is the justification of using the instrumentation amplifier. Okay. Now let's look at the output of the instrumentation amplifier when the input, the differential input is connected to it. Okay, so VBD is now connected to the circuit, to the instrumentation amplifier, and now I am varying the temperature over this range, 10 degrees, roughly about 12 degrees to about 35 to 40 degrees Celsius, right? No, it's a bit more than 35 degrees Celsius, but a bit less than 40. So I have varied it over this range, and I measured what is the VBD coming out of the instrumentation amplifier, the amplified voltage. And what I see here is, it's very nice to see that there is a linear relationship between the temperature and VBD. A linear relationship is always preferred, it's not always guaranteed, but in this case we do have it, so that's pretty good. And the voltages are now, again they are measured using only the multimeter, so I'm not using any Raspberry Pi, I'm not using any advanced measurement technique. I'm just using the same multimeter which I used earlier. It has the same 1 millivolt precision, but because now I've amplified the signal, I'm able to get a lot more points with a higher degree of precision. Okay. Now there is a drift in the voltage which is of the order of 3 to 4 millivolts. This can be useful for calculating what is the error in the measurement data. Right. Now there is a linear relationship between the temperature and the voltage, and this is expected because one, the PT100, the resistance of the PT100 varies fairly linearly with temperature over a large range, so that is number one. And number two, the Wheatstone bridge the resistance does not vary so much that the Wheatstone bridge output goes into the non-linear range. Okay, so if you remember the transfer characteristic of the Wheatstone bridge, it can be in general non-linear, but if the resistance variation is fairly in a small range, then you can approximate that transfer characteristic to be linear. So that is what we are seeing here. The transfer characteristic is linear with the change in temperature. Alright. And we also have a blue line fit here. So this is the linear fit, and the linear fit parameters are given here. And what we see is we do have an offset. Right. So ideally, because we are using a Wheatstone bridge, the Wheatstone bridge in its maximum sensitivity configuration, and we also know that at T equals to 0 degrees Celsius, the resistance of the PT100 is going to be 100. So all the arms are going to be balanced. So if the Wheatstone bridge is going to be balanced, that means that VBD should be 0. So ideally this straight line should have passed through 0. Right. But what's happening here is that's not the case. Okay. So what you are seeing here is there is an offset, and that offset can arise due to some experimental considerations which we'll discuss later. Okay. But the important thing is you have a very systematic and a highly linear transfer characteristic between VBD and temperature. Okay. Now what we are going to do is we are going to connect the ADC to the instrumentation amplifier output to the ADC. And for this we will utilize the connections which is provided in the GPI 0 read the docs online document, right? So if you remember in the first class I was saying that if you understand how this very basic configuration works, that you have a potentiometer, that potentiometer is now connected to the MCP3008. So you are converting a real world analog signal to a digital signal using the MCP3008. And that is what we are going to do exactly here, right? So what we are going to do is we are going to replace this potentiometer, which is an emulation of an analog signal, with the input from the instrumentation amplifier. So we are all coming to a full circle now, alright? And that's what we are going to do here. So the connection to the Raspberry Pi for the MCP3008 is exactly the same. The only thing is now we are connecting the output of the instrumentation amplifier to channel 0. Okay. So now what we have done is we have finally realized temperature logging with the Raspberry Pi. So what you are seeing here is the analog signal coming from the instrumentation amplifier being read by the MCP3008 and being extracted using the Raspberry Pi using a very small piece of code, right? So on the x-axis you have got the temperature variation, and on the y-axis you have the bit level output of the ADC. So you can get a scaled output from the ADC. You can write a simple code for that too. It will give you directly output in voltage, but it is more illustrative and instructive to actually see what is the bit level output coming out with the variation in temperature. So here also we see that there is a very nice linear relation, right? So the output bits, there is a 10-bit ADC, you have got output ranging from 0 to 1023, right? And there is a linear relation here also, which is good news for us, which means that the ADC is working fine and it is operating in the linear range of the ADC. Here we do have the linear fit parameters, which is M is 20.53 and C is 167.2, and this C is indicative of this offset, right? So you have this offset here. Now the important thing is, once we have made this measurement, the question naturally arises, what is the precision with which we have made this measurement, right? So that is also one of the reasons why I have decided to give this output in bits, because when you are observing the output on the Raspberry Pi, you can actually see the bit variation happening, right? So it's not going to stay at just one bit level for the VBD, because you have got sources of noise coming in. There can be some variations in temperature, maybe some wire is moving somewhere. So you have a slight variation in the bits, and that drift in the measurement is of the order of 4 bits. So which means that if we are looking at this particular measurement has got an error bar of the order of 4 bits. Now if it has got an error bar of the order of 4 bits, you can use the linear fit relation to estimate what will be the typical error in the measurement, right? The typical error in the measured value of temperature. So that turns out to be of the order of 0.2 degrees Celsius, okay? Because you can use this value, and from there you can estimate using this drift measurement the uncertainty in temperature. So that's 0.2 degrees Celsius. And if you compare it, that is also the offset that we observed earlier. This offset is slightly higher, and this could be because over the duration over which we have made the measurement, there might have been a systematic shift somewhere. So maybe a wire moved somewhere, because at the end of the day it's a very crude setup. So the wire might have moved somewhere, which would have resulted in a shift in the characteristics, right? So there is still an offset, and that offset is still in the negative direction. Okay. Now, if you compare this measurement with the earlier multimeter measurement, so let's do a side-by-side comparison, you can see that we have got an improvement in resolution by a factor of 10. Okay. So we have been able to achieve a higher precision in measurement, right? And compared to 2 degrees of resolution here, we have got 0.2 degrees of resolution. Okay. So we have a resolution enhancement. And just to give you a glimpse of what the actual experiment actually looked like, I'll upload this video separately. So you can actually see that here I have turned down the temperature, so the temperature is actually decreasing and it is approaching towards a set point. And while it is approaching towards a set point, the bit values are also steadily decreasing. So this is illustration of the fact that the ADC is actually able to recover this temporal variation in the temperature, right? Okay. So what did we learn from all of this, right? So the primary goal of this experiment was to teach you how to design a system, not just individual blocks, but a system. When you are designing a system, you cannot just consider how each block functions, but you have to consider how the whole chain is going to fit together, okay? And the strategy that I told you here is you work your way backwards, okay? And that kind of works in most of the cases. And what happens is, even if it doesn't work, you will surely identify the bottlenecks in each part, okay? And then you again rework your system. You again go back and say, okay, if the last block is not the bottleneck, where is the bottleneck? And then you work your way sideways from the center outwards or from the left to the right or whatever. But you'll be able to identify the bottlenecks, okay? Then the other thing that we are seeing here are design trade-offs. So this is like the bread and butter of engineers. There is always a trade-off. You cannot get everything. And particularly what I mean by design trade-off here is, now you can in principle extend the temperature range. I limited the temperature range to 0 to 40 degrees Celsius because that was the range over which I was able to comfortably adjust the temperature of the Peltier, and I could illustrate the essential principles of the system design. You can extend the temperature range, and you can do that by adjusting the gain of the instrumentation amplifier, because it's all about making sure that you are able to adjust, or you are able to record all the variation values within the range of the ADC, right? So as long as it is within the range of the ADC, you are able to quantize it and you are able to get the digital value of the temperature. But this also means that you could have a loss in the temperature resolution. So for instance, if you want to measure to 50 degrees Celsius or maybe even 100 degrees Celsius, you will have to make sure that that 100 degree range is within that 1024 values, right? So that means that you have to bring down the gain. If you bring down the gain, you are able to cover a larger range, but then the temperature resolution drops, okay? Because you only have a limited number of bits, 1024 bits, okay? So that's a design trade-off. Now the experimental conditions. So here, this was a very crude setup, right? So if you really wanted to make a temperature logger, making sure that the errors are minimized, you would build it on a PCB, that is one. The second thing is you would shield it properly, you would make sure that things don't move here and there, you would make sure that the voltage is stable and all that. But given the experimental conditions, what we see is the thermometer, which was also used to record the temperature, it had a least count of 0.1 degrees Celsius. So there is already an uncertainty there. That is the first uncertainty. And the second uncertainty is also the way in which we mounted the thermometer on the Peltier. So if you remember from our lectures, we talked about there can be an offset in the measured temperature if you don't mount the thermometer properly. Okay. So most likely that is where the error is coming from, because we have not properly isolated the temperature sensor from the environment. Ideally you should only record the temperature of the device that you want to measure, but because the other end of the resistor, of the thermistor, is pointing upwards, or the thermometer is pointing upwards, it's not isolated from the environment, and perhaps that's why you are observing an offset. But again, if you know that this offset is going to be conserved at all times, you can calibrate for that, right? And you can remove it. As we saw that we have got a good precision, it's just that it's not accurate, but then the readings are systematic. So you correct for the offset. And one way of correcting for this offset is to make a resistance based calibration of the Wheatstone bridge. Okay? Because at the end of the day, the differential voltage VBD is a function of R, right, of the unknown resistance. What we are doing here is, because we have access to the Peltier, we are varying the temperature of the Peltier, and from there we are getting the transfer characteristic. But what's happening here is, if you calibrate with respect to the resistance, it can be in any configuration. Essentially what you are going to get then is, you are going to get a Wheatstone bridge which is calibrated and is able to give you an output in the range of 0 to 3.3 volts. Now you can replace that PT100 with any other strain resistor. You will have to adjust the circuit a bit, but you will be able to use the same configuration for a lot of things, because you are not doing with respect to temperature, but you are calibrating with respect to resistance. Okay? So the offset issues can be potentially avoided, but then there is a catch, because it calls, especially for the case of the PT100, it calls for, you need some other calibration from somewhere else. Okay? What this means is, I have calibrated the Wheatstone bridge with respect to the resistance. If I am using the PT100, where the resistance varies with temperature, I will have a very good value of the value of the resistance. VBD versus R I already have, but I don't have R versus T. The R versus T graph has to be provided by the manufacturer. But these are also very well, so if you get a good quality PT100, you get a data sheet with it, you can rely on the data sheet parameters to a high degree, right? So that is another way that you can avoid the offset. Yeah. So yeah, so that's basically the lecture, and that basically has what I hope that I have been able to impart to you the essence of system design, how you actually work with a system, how you design a system, not just looking at the individual blocks, but looking at the system as a whole, and how to analyze the performance of such a system, where the errors can come from, how to kind of dig deep and try to make it a better one, right? So the system is ready, it is actually in the lab, and you're more than welcome to have a look at it. So just pop me a line and then we can figure out a time to work with it. Or because all the system parameters are fairly well defined, you can try to replicate the system by yourself. So if you want to work on the system, let me know, and we can fix a time to work on it. Alright. So thanks for your time, and I'll be uploading the report which I made for this particular experiment on Moodle. So you can have a look on what is the kind, how do you present this data also. Alright. So thanks a lot, and see you soon. See you in the next class. Bye.